I'm Daniel Firestone. I am the tech lead manager for the Azure Networking Host SDN team, and that means, yes, as all the virtual switch, the NIC, and the whole platform that makes SDN on the host run in Azure. So what I'm going to talk about today is a little retrospective on 8 years of shipping host SDN in a public cloud environment at scale in Azure, focusing on the virtual filtering platform, or VFP, our major contribution in the space. So what I'm going to talk about today, I'll start with what is Azure, a little bit of scale. Why do we want virtual switches for SDN, and why is vSwitching a scalable way to make SDN work? Give you a little history about some early implementations of Azure's host SDN stack. I'll talk about some of the goals we had when we decided to create a unified platform in VFP. Talk about the platform itself, and then how we address some of the challenges of scale, how we built hardware offloads over time, and then conclude with a bit towards the future. So what is Azure? Well, I borrowed some slides from the marketing people to help folks. We are a cloud services platform. We provide infrastructure services like VMs and cloud storage, data services like Hadoop on top of it, app services, cloud and mobile services on top of that, the SaaS layer. We're fairly global. This is one of the better marketing slides I saw. We've expanded over the years. Here are the number of Azure regions in 2013, and every year we add more regions. Each of these regions have multiple data centers in them very often. Some of them are multiple campuses even, and every year more show up. We're all over the world. More will be announced this year. I think we've already announced a couple more in France. Since we launched in 2009, late 2009, beginning of 2010, we've gone from maybe 100K compute instances to many millions. We watch storage grow from a few petabytes to many exabytes. The data center network has grown incredibly fast, from tens of terabits to petabits. And in fact, these orders of magnitude are actually too low. I could go beyond that. Who uses Azure? Well, it turns out that our biggest customer base are enterprises. So we have many startups and ISVs as well on our platform, but over 85% of the Fortune 500 are on us. Here are some various numbers the marketing folks have discussed, but we basically have a huge amount of scale, huge numbers of customers. It's growing all the time, and enterprises are moving and shifting gigantic on-premise data centers into the cloud. So for all this, why do we need virtual switch SDN policy? Well, in a word, policy application on the host is more scalable, and that's one of the things I really want to try to convince you over the course of this talk. The first example I'll give of why we want to use host SDN is a load balancer. And I'll use the example of Ananta, a paper we did at SIGCOM in 2013. All infrastructure and most of these types of cloud applications runs behind a load balancer, enable HA application scale. So how do we make application load balancing scale to the cloud? There's some challenges with this model. How do you balance your load balancers, especially with traditional hardware LBs? They can be very expensive. They can't support the rapid creation and deletion of load balancer endpoints that are required in the cloud. You have to support tens of gigabits per cluster and need a simple provisioning model. And sort of classic hardware-based appliances aren't very good at this approach. So what's the SDN approach to this? How do we do this in software-defined networking? Well, we build a software load balancer with a NAT and the vSwitch. What is a load balancer? At the end of the day, you map a virtual IP to a dynamic IP. So you have a NAT. And then you're making a decision across those different IPs of which one to load balance to. Now, traditionally, a hardware load balancer would take that sort of muxing function across IPs in the NAT and package them together. In the software approach, we move the NAT down into the vSwitch itself on top of the VMs. What does that enable us to do? Well, one, it makes the muxes stateless. Right? We can have these sort of muxing devices and scale out as many as we want, and the state isn't on them. And it enables direct return. We don't even have to send traffic back. So our return traffic from the VM goes straight back to the internet or wherever it came from. And then we can have a single SDN controller, in this case an SLB controller for the software load balancer, abstract out all these LB and vSwitch interactions. Second example, VNet. The idea is here really based on the VL2 paper and some of the stuff that was explored in Microsoft research back then. The goal being map customer addresses, a BYO IP address space, to provider addresses, 10/8 addresses that we would actually use on the physical network itself. It requires translation of every single packet on the network. It does mean that companies can create their own virtual networks with their own IP addresses, their own topologies, security groups, middle boxes, network functional virtualization, bring their firewalls, create a network in the cloud that looks just like their on-prem network, or if they're defining a new application that meets the needs of that application itself. But how do you do all this policy? Well, for example, if let's say you're forwarding traffic back to on-prem. We have a green network and a blue network. They're running behind the same VM switch, so we're going to use encapsulation to take traffic from a green network running in customer address space and encapsulate it into a physical address space. VM switch will do a policy lookup based on routes and encapsulate a packet that's sent out from, say, this green VM off to a gateway, and that gateway can then do IPsec back to an on-premise network. This is an example of how you might insert an appliance into your network. Even more virtual switch policy. 5-tuple ACLs, stateful firewalls. We do billing this way. We do rate limiting this way. Our security guards happen this way. And there's more in development all the time. So what did our early approach look like? When we first launched Azure, we started by sort of stacking these drivers in the vSwitch itself. You write new code to do a new SDN application, like stateful firewalls were the first one we launched in 2009. Then we did load balancers. Then we did VNet later. And you would go write a new driver module, hard link it into the vSwitch, and ship an OS update to the platform. So it's sort of before the explosion of sort of programmable vSwitches or match action tables became really popular. And this was revolutionary for us in that it allowed us to ship applications like the ones I talked about, but it wasn't very easy to add new SDN apps. The moment we kind of did this, everyone wanted to add more of these apps. And the notion that you're going to write new kernel code every time you want to change something in the SDN stack isn't really what you want. So after a couple of years, we decided we needed a more flexible host SDN platform. And that's really what I want to talk to you about today, is what were the goals of that platform and how did we build it? So originally, we had 3 goals when we started this project to create a unified platform for host SDN. The first goal is to provide a programming model allowing for multiple simultaneous independent network controllers to program network applications. If you've ever worked with some of the open source projects in the space or some of the more typical commercial projects like OpenStack or OVS, all of which are very cool and allow you to do a lot of this policy, you'll note that they typically have kind of these very single controller models. Like OpenFlow is designed around the notion that you have a controller and it comes and pushes state. Well, actually, what we discovered is if you want to create new SDN applications all the time, you don't want to go modify the same SDN controller to have to make all those work. You want to have a model where, say, our VNet example that we gave and our load balancer example can be 2 completely independent controllers. We can converge those policies. Second goal is provide a match action table model. We like the idea of match action tables, like what people were working on around the same time with OpenFlow and stuff like that, but capable of using connections as a base primitive instead of just packets. The idea that you could have stateful match action rules as first-class objects in your match action language. Because as it turns out, most customers want to program policy based on connections, right? Nobody wants to say allow inbound TCP packets, but outbound TCP packets are blocked because then you don't get a connection. You'll never get an ACK back. You want to say allow inbound connections, but don't allow outbound connections, say, for example, or vice versa. And the reason sort of, you see that maybe OpenFlow or models like this have that model is because it's based on the notion of a physical switch where you can't keep that kind of state in the switch ASIC. But if you're in the host, you actually can. And so we wanted a map model that supported this natively. Our third goal was provide a programming model that allows controllers to define their own policy and actions rather than implementing fixed sets of policy. So what is VFP? This is our SDN data plane. It's the virtual filtering platform. It's a plug-in model for the virtual switch. It basically replaces the Hyper-V virtual switch with its own policy and provides all this core SDN functionality we're talking about with programmable rule flow tables. And the basic model is to take standard sort of switch notion of L2 extensibility. You have an ingress flow and an egress flow, into your bridge and out of your bridge, and translate that into something that's more L3-like. Policy that's inbound to a VM and outbound to a VM. Coming back to our example of sort of billing, ACLs, VNet, and load balancer, which I'll come back to multiple times in this discussion, create those as layers where you have this policy sitting on a VM stack itself. And the goal here is that all the policy is in the controller and is not hard-coded into the switch. VFP will be a fast and flexible implementation of policy. And in order to do so, we exposed 3 key primitives to controllers in our programming model. One is layers, the notion of independent flow tables that different controllers can program and have an ordered pipeline between those controllers and their policy. The second is rule matches, right? In the match action table model, define which packets match which rule, and then the actions associate what to do with a packet for a given rule. All right, so what does a match action table look like? It is ultimately a layer per policy. I can come in with a VNet description and program a VNet flow table that can be in series with a 10 description that creates, NAT endpoints in a load balancer or ACLs. And different controllers can come in and program policies in VFP in series on top of a given VM. And the programming model is really per VM based. These layers are not built-in functions. They can be created at any time. It's only a load balancer layer, a VNet layer, based on how it's defined. You can create these as arbitrary objects and sort of program them with policy on the fly. And you can add resources to them if you want to do sort of more advanced policy lookups like hash table lookups. And you can look at the paper for more details of how sort of those work. Everything in VFP is stateful. The core primitive of most policy is a TCP or UDP connection. And so the way we implement that is that within these layers, in addition to the rule tables that you can come and program individual rules and match action tables, we keep internal flow state and flow tables of each and every TCP connection so that we can reverse the action on the way out. And these stateful rules make it really easy to reason about asymmetric policy because rules apply to whichever side of the started the flow. So if you have a stateful ACL, it'll say, allow inbound TCP connections in the inbound rule group. And then that can go and create, when it's matched, an outbound flow in the outbound flow table that says, hey, for any packets returning on this 5 tuple, allow that back out. Let me give you an example of what this means, because I know that can be a little confusing. We take a software load balancer. That load balancer, we said, had to do 2 things. It had to do muxing, which means it's effectively encapsulating packets to a given destination, and then it's got to do a NAT. So we can model that as 2 layers. The load balancer can create a decap layer that is taking those encapsulated packets from muxes in and decapsulating them, and then the next step out is towards the VM is running that NAT. That NAT creates flow state, which is controlled within that layer, and that action will be reversed on the way back out. And then we can sort of stack these accordingly. One cool use of these stateful flows that I wanted to give an example of why is this flow model so useful. Let's say we want to create a fast path for a load balancer. Normally, if 2 VMs behind or 2 services behind the same load balancer want to talk to each other, they have to go through a MUX because a VM sends a packet to a VIP, which goes to a MUX of another VM or another service, in this case our storage service, and then gets natted. In this case, we can have the MUX detect that the source is in our network, send VFP an in-band control packet, create a flow that basically says, for everything after the first packet that comes out, well, I've load balanced this TCP connection to this VM, and so send it directly along the way. So you can create all sorts of policy like this. And there are many example layers, and this was all successfully deployed back in 2012. One example was when we wanted to create a new load balancer in VNet space instead of PA space. We were able to go create that without changing VFP by simply defining a new layer on the fly. So let's talk about challenges of scale. Our NIC speeds have scaled up. We started with 1 gig adapters, 10, 40. We're at 50 now, what we're deploying. We're going to 100 soon. So over the years, we got a 50x improvement in network throughput. We did not get a 50x improvement in CPU power to go with it. And so you can't just directly scale the same kinds of policies we're doing. So the major goals for VFP v2 were provide a serviceability model allowing for these sort of frequent deployments without requiring reboots or interrupting connectivity for stateful flows. I'll describe this in detail in the paper. It's a little much to go into here, but doing those sorts of updates is pretty common for us. Another goal is provide very high packet rates via extensive caching, which I will talk about. And finally, we want to implement an efficient mechanism to do hardware offloads. The challenges with these layers were, this is kind of a holdover from that original vSwitch design I talked about. Each layer is independently taking packets and parsing them and modifying them. And as host SDN became this very easy concept, people added new layers and new SDN policies all the time. And there was no way we could keep up with sort of adding layers and scaling up at the same time. So we needed a better primitive. We created the notion of what we call our ASIC pipeline model, which says, well, treat this just like you would in a switch ASIC or something similar. Instead of modifying a packet each time, push metadata around. Parse the entire packet. We have a single unified flow ID when a packet comes in, and send metadata to the layers and let the layers send us transpositions of what they want to do with the packet, which will compose over the course of all the layers, create a single action, and modify it at the end. And anyone who's seen kind of switch designs will be very familiar with how this sort of thing works. I won't go through the details of how the actions are defined, but you can create sort of composite actions on top of them. You can create unified flows with all sorts of match fields on top of them, and all the details of this are in the paper. One of the cool things you can do with this now is once you've created this notion of a flow ID that comes into VFP and all that policy in between, you can create a single fast path that caches all the actions across it. And because we've mapped everything to an action, including encapsulation, we don't have any tunnel interfaces or VTEPs or stuff like that you have to forward into, you can actually compile all the actions your vSwitch will take into one flow and one action and cache it accordingly. And so we have this fast path through VFP where the first packet may go through all these different layers of a flow, but everything subsequent will take a single hash lookup and a single action and go out the pipe. And that's kind of how we scaled. So let's talk about hardware offloads. So what's the ultimate hardware offload for something like a virtual switch? Well, if we can get I/O virtualization. Our NICs are capable of defining virtual functions inside the VM and doing hardware processing directly into those VMs so that VMs can send packets without going through the host at all. We could save lots of CPU, lots of latency, lots of throughput. But where does the SDN policy go in this model? And this has been a problem for all the NIC vendors trying to push SRIOV and related strategies for years. So the latest big thing that we've done is we've accelerated VFP with our own smart NICs. And you may have seen some announcements that Microsoft has done about this, that we're actually putting, and have been for the last couple of years, putting FPGAs, programmable hardware devices, into every single server and using them as NICs. And it turns out that this language we created for unified flows and these header transpositions maps perfectly to what you want to do in a NIC. In fact, I have one here, and you guys can come find me later if you want to see one. These are the ones we deploy today. And you can't easily create all of your sort of complex match action table policy in lots of different layers in hardware. Right? That's not really going to be scalable because that's too much matching to reasonably do. But you can take those unified flows and push them off to hardware because that's just a gigantic hash table. Right? That's just it's a cache of all the flows in the system. And so we create a scheme where the first packet of any flow comes through the software path. We then offload it to the FPGA, and we can add new actions to the FPGA on the fly as we add new actions to VFP. And then every subsequent packet flows through the FPGA and directly into the VM. And subsequently, we get great latency, we get great throughput, nothing goes to the host at all. And this is really, to me, the future of where host SDN is going. And if people here are thinking about new research directions or opportunities in this area, I would encourage people to think about this. What are going to be the new hardware-software co-design models? We've proven that host SDN is this very scalable platform to do this kind of policy. Every major public cloud, all the big players have adopted something host-based. The strategies are a little different across the different companies, but this is the base strategy everyone's using, and everyone has to scale it up. And so everyone is thinking about new offload models, new hardware-software co-design models. We're doing FPGAs. Other folks have bought ASIC vendors or doing other internal projects. And what will these sort of models look like in the future? How are we going to do programmable acceleration for transports, RDMA, programmable QoS, crypto, and more. So the results of this, so Azure Accelerated Networking, which is the service that runs on top of FPGAs and VFP and all the stuff I've talked about, we believe, based on our measurement, basically gives you the fastest cloud network in the world. We give you 25 gigabit VMs of network in addition to the rest of the NIC going to storage capacity. Consistent low latency performance. I mean, we can consistently get over 25 or less microseconds, and even in tail latencies of TCP stacks between VMs, as long as they're within kind of a placement group. That's been huge latency improvements, packet per second improvements. We get the programmability of the software stack of VFP. Controllers can come add new policies all the time to VFP, but we get the performance of a hardware solution. And so that's what we think is kind of a cool result of this. And if there's one idea I want to leave you guys with, it's that the reason host networking has been so successful for us, for others in this space, is it ultimately does make the physical networking fast and scalable. I mean, there's a lot of focus in the community about cool things we can do with switches and programmable switches, and all that is really interesting. But ultimately, you'll never get the scale of the kind of policy that you're going to do per TCP connection policy on, which you need to do stateful firewalls, you need to do stateful NAT. And so we can build, because of host SDN, this massive distributed 40, 100 gigabit network and have no hardware per tenant ACLs, no hardware NAT, no hardware VPN, no vendor-specific control management or data planes. These are all sort of merchant silicon-based, really fast switches. And that's okay because all the policy is in the host. Everything is a VM. All the appliances are VMs. Everything's in software. And network services are deployed like all other services. And the last cool thing I want to say about this is it turns out that VFP, which is battle tested in the cloud, is now available in Microsoft Azure Stack for the private cloud as well. So thanks to the many VFP developers who worked on this project over the years, architects who influenced us, and Dave Maltz, Mark Rasinovich, and Albert Greenberg, who have been leaders in the group and sponsored this over the years. And the slide that paid for my trip out to Boston, want to come build the next generation of host SDN stacks? Send me a note. We're hiring. Thanks, guys.
Marco Canini from Kaustin. So thank you very much for the very nice presentation. I have a question, which is nowadays we're moving to containers in the cloud, and you talked a lot about VMs. So do you see this as being a challenge in switching to, say, several orders of magnitude more virtualized functions and host running code?
Yeah, so I see it as only pushing this kind of scale challenge further in terms of the kind of flow state requirements we need. I mean, so we run the Azure Container Service today, which is very popular with our customers, which allows them to create, Docker, Mesos, or other managed containers inside their VMs and big services on top of that. And we have lots of customers doing container deployments. And yeah, it just pushes flow state further. I mean, you still manage policy in similar ways, right? In terms of containers, now it's a per IP address policy instead of a per NIC policy. The policy itself looks similar in the vSwitch. You're doing NAT, you're doing load balancing, you're doing ACLs, et cetera, but you just have more. And so you really need to be at the scale of host SDN to make stuff like that work. But it is absolutely tractable. I mean, you talk about doing this policy in hardware. Why can you do this on a NIC like this? Well, this is a 50 gigabit NIC that we deploy, and that means I can attach DRAM to it and run all my policy out of that. And it's pretty cheap to put a few gigs of DRAM on a NIC. But you try to put that, somewhere else in the network, and well, now you need SRAM. If you're at any kind of aggregation point, you're not going to get that kind of scale. So yeah, I do think containers are pushing further in that direction.
Thank you.
Hello, a nice presentation, Mehrdad Moradi from University of Michigan. So in some cases, we need to perform per packet policies, like deep packet inspection, where we need to inspect every single packet to find a certain signature. In this case, how does the caching mechanism that you described in the pipeline would scale? That's my first question. The second question is that these days there are other smart NICs, like these Netronom NICs, which allows you to write P4 programs in addition to C++ program and combine it and define new switch actions and packet headers and push it into the NIC.
Sure.
So how is it different from these NICs?
Sure. So I'll take the NIC one first. FPGAs are a different level of programmability, but there's been a huge explosion in interest in the notion of programmable NICs because of these sorts of policies being deployed, which I think is great. You know, models that some of the ASIC vendors like that have are a little bit more restrictive in terms of, you know, how you're able to sort of attach your data path. If you want to do scheduling based on sort of things you've parsed or actions you've taken, it's a little bit harder. It's not quite the same degree of flexibility. And so we have seen that we can scale using FPGAs for what for us is something that's cheaper and more efficient and allows us to construct a design that just has the policy we need and not sort of anything else. Actually, sorry, what was your first question again?
The caching mechanism in the case of per packet policies.
DPI. DPI workloads are something that we just don't see as being very scalable to put in vSwitches themselves, and so we typically do that in kind of appliances in the NFV model. And if we need to push stuff like from the internet through DPI, we'll push them through appliances with sort of those BYO topology rules.
Okay, thank you.
Okay, 2 quick questions.
Leonid Ryzik, VMware Research. So how does your hardware acceleration work with the stateful policies?
Mm-hmm.
Do you maintain the state and the hardware to go to the host?
Right. So the idea is that the stateful policy is maintained in the vSwitch itself, and there are more details of this in the paper. I'm sorry I didn't have time to go into it in detail, but what you're offloading from software to hardware is per TCP connection state. What hardware is maintaining is a giant cache in cheap DRAM of, you know, potentially millions of individual TCP connections and actions associated with them. And those actions were computed using that stateful policy out of the vSwitch and programmed as, say, TCP SYNs came through down to the FPGA so that subsequent packets all flow through the hardware.
Very last, very quick.
Okay. Are you able to nest ACLs and depending on the network layer that's going through?
Yes, you can create either multiple layers of ACLs or you can sort of nest them in groups. A couple examples that I described in more detail in the paper if you want to take a look.
Okay.
Thanks, guys.
Thanks.